Finally, our phenol question, 2-methylphenol or 2-methylphenol. Any methylphenols are cresol, and this 2 means that the methyl group's next to the phenol, which is the ortho position. So instead of 2-methylphenol, we can call this orthocresol. It's an acid with a pKa 10.32. First thing, draw its conjugate base, and using resonance structures explain why it's an acid. Well, here's the conjugate base where we've lost that acidic proton. So we've got minus charge on the oxygen, which we're indicating by showing this oxygen actually has, of course, 3 lone pairs, but I don't really care about the 1 lone pair as shown. Now, in the same way that phenol is an acid because it can delocalize this negative charge, our 2-methylphenol can do the same. Okay, so we can take this lone pair, and as these are electrons in a p orbital, they can get tied in to the pi electron cloud of the benzene ring. So the first resonance structure that we would do, starting here, is to take this lone pair and put it into the oxygen now, making a double bond to this carbon, at which point carbon 1 says, well, I don't need those electrons anymore. Carbon 2, why don't you take those? So now the negative charge is put on carbon 2 as well. So we're sharing the negative charge already between the oxygen and carbon 2. Carbon 2 can say, I've got this bounty of electrons, why don't I share them with carbon 3? At which point carbon 3 tells carbon 4, get lost and take your electrons with you. So now we've got this resonance structure in which the negative charge is on carbon 4. And carbon 4 can do the same thing and say to carbon 5, share my electrons with me, at which point carbon 5 will say to carbon 6, take those extra pi electrons yourself, put the negative charge there. So as we saw in our notes, charge spread out, thus the conjugate base is stabilized, enabling this to be an acid. Now I'm going to point it out here, although this is part of the answer to the next question. This resonance structure here is not as good as it would be in phenol without that methyl group, or as good as this one or this one, because this methyl group here, of course, is a positive induction group. It pushes electrons towards whatever it's attached to. So the methyl group here is pushing electrons in towards carbon here. Okay, just as that carbon also has this negative charge on it, which means that this resonance structure is not as good as these other ones. Now, because one of the resonance structures isn't as good as phenol, 2-methylphenol is not as good an acid as phenol is. And you can tell that if you remember the Ka or the pKa of phenol is about 10. So remember, the bigger the pKa, the weaker the acid. 2-methylphenol is a weaker acid than phenol. Still an acid because it can spread out the negative charge, but one of the resonance structures is not as good because you have this methyl group pushing electrons in towards a carbon that's already got too many electrons. Now let's draw the structure of metacresol, and there is, of course, metacresol, which you would otherwise call 3-methylphenol. Meta means that there is 1 carbon separating the 2 groups. Now let's rank in order of acidity phenol, 2-methylphenol, 3-methylphenol, and 2-nitrophenol. There's 2-nitrophenol, so now we've got all of the structures we need. Okay, well, the first thing to think about is that the methyl groups, as we said, are positive induction, thus they're pushing electrons into the ring. And 2-nitro, however, nitro is negative induction, it's pulling electrons out. Now, seen as how in terms of acidity we're putting an extra electron into the ring, the more that we can share that electron density, the more that we can spread it out, the better the conjugate base, the more stable the conjugate base. Okay, so therefore the nitro group, which can suck that extra electron density out, is going to be better than the phenol, but then the methylphenols, which are pushing electron density in, are going to be worse than phenol. Now, as far as the 2-methyl versus the 3-methyl, we've already seen the 2-methyl is going to rely on this particular resonance structure here with electrons being pushed in, so this is not as good. When we have the 3-methyl, the metacresol, there's not actually a resonance structure that has the extra negative charge on that carbon 3. So therefore 2-methyl is going to be nastier than 3-methyl. So the 3-methyl is a better acid than the 2-methyl. So the overall ranking: nitro best because it's sucking electron density away, phenol because it's just phenol, and then of the methyl phenols, 3 is better than 2 because that 2-methyl phenol actually has a resonance structure where the methyl group is directly in conflict with that extra electron density there. Hopefully this all made sense.